Hello students, welcome back. In the previous videos, we talked about linear combinations and generators. And now let's talk about linear independence. We begin with n vectors, v1, v2, all the way to vn, from a vector space capital V. We say these vectors, v1, v2, v3, all the way to vn, are linearly independent if the linear combination 0 means all coefficients are 0. There's no way you're going to get linear combination equal to 0 with some non-zero coefficient flying around. Linearly dependent, on the other hand, some non-zero numbers are possible. So there may be 3 non-zero numbers, the others are all zeros, or there may be 17 non-zero numbers and the others are all 0, or maybe all 10,000 numbers are non-zero, yet linear combination is still 0. There can be various, typically there are infinitely possible choices. In that case, linearly dependent. Now, linearly independent means linear combination 0, then all coefficients 0, vice versa. 0, 0, otherwise non-zero. Example. Okay, let's consider some standard unit vectors. 1, 0, 0, 0, 0, 0, those kind of thing. And then only the second component is 1, otherwise all 0. And then third, fourth, fifth, all the way to the last one. These are linearly dependent. How do I do that? Well, let's see. If you take linear combination x1 e1 plus x2 e2, you see, you can easily see those from this color coding. Even without color coding, it's not too difficult to see because first vector just takes first coefficient and then the others are all killed. Second vector here takes the second coefficient and then everything else is killed and so on. And we have this kind of expression. So if this thing turned out to be 0 vectors, so it should be capital O, by the way. So this is blue, that's red, all the way up to this green, is a 0 vector 0 means all vectors, this thing, is equal to all 0. So yes, x1 is 0, x2 is 0, all the way to xn is 0. Oops, incorrectly copied. Okay, how about some other examples? U, V, W given by 112, 3, 181, 7, 187 are linearly dependent, it says. Is it possible to prove it? Well, let's see. Let's do that. Let's set it up. So x u, so 1, 1, 2, plus y v 3, 1, 81, plus z w 7, 1, negative 7 is 0, 0, 0. Okay, let's set it up. And then here goes the first coordinate. X plus 3y plus 7z is equal to 0, okay? And then x plus y plus c equal to 0, isn't it? That's coming from the second coordinate. Okay. And then 2x minus y minus 7z equal to 0. Did I get all the equations correctly? First, second, third. I hope there are students in person so that they can find out my mistake, if any, on spot. But me, I'm doing alone, so I cannot find mistake. Maybe I'm right, maybe I'm wrong. Let's find out soon. And then let's work this one out. If I add the first and last, looks like I can kill up this 7z. So let me add these two. So x plus 2x, so 3x plus 3y minus y, so 2y is equal to 0. Good. 7z, negative 7z, that's gone. That's what I got from first and third. And then, okay, this was the second one. Okay. And then how do you work these two out? From here, can I solve for x? I guess I can solve for x. So x is equal to negative 3x is equal to negative 2y. So if I divide by 3, this is what I'm going to get. Did I do this right? Okay, that's what I got from here, here combined, and then that. So let's put this one into second equation that I didn't use yet. So x plus y minus 2/3. Excuse me, the other way around. X is negative 2/3 y plus y plus z is equal to 0. So 1/3 y plus z is equal to 0. So therefore z is equal to negative 1/3 y. Is everybody with me here? So, okay. Therefore, I'm getting x, y, z. X, y, z is, let's see, negative 2/3 y and arbitrary y, and then negative 1/3 y. Okay, all right. And then y can be arbitrary, so I can put in any number I want. And strategically, I'm going to put in y equal to 3 in order to kill off all those denominators. So x, y, z will be negative 2, 3, negative 1. And that says here x, y, and z are negative 2, 3, and negative 1. There, this is negative 2, that's 3, and then that's negative 1. Is this true? If true, then we are done. So negative 2 plus 9 minus 7, yeah, that's good. Negative 2 plus 3 minus 1, yeah, that's good. Negative 4 minus 3 plus 7, yes, true. Turns out okay. Oh wow, that was highly unpleasant computation, but it can be done. Yes, we use brute force computation to prove that these three are linearly dependent simply by setting up and then finding out x, y, and z. How about the next example? Function e to the t power, e to the 2t power, and t times e to the 2t power are linearly independent. What do you mean by that? So if I plug in x e to the t power plus y e to the 2t power plus z e to the 2t, no, t times e to the 2t power if that's going to be 0, then we have to have x, y, z has to be all 0. Well, why is that? Well, this is equal to 0. As a matter of fact, here we're dealing with function space. This is basically the set of all continuous real function, if you want continuity, or set of all infinitely differentiable real functions. These are all functions we are talking about. So 0 vector here is a 0 function. So constantly 0 for arbitrary t value. So what am I going to do here? Plug in t equals to some number, like 0, t equal to 0. If I put t equal to 0, then what do I get? X e to the 0 power is 1, good. Y e to the 0 power is 1. Z times 0, so that goes out, that equal to 0. That's what I'm getting. What if t is not 0? 1? Okay, in that case, I'm going to get something more complicated. X times e to the 1 power, ex, and then y times e squared, and then plug in 1. Looks like I'm getting second equation like this if I plug in t equals to 0. Okay, and then, alright. What if I plug in something still different, say negative 1? In that case, what? E to negative t power, so this is negative 1 power, and this is negative second power, and then t is negative 1 there, so this should be minus. So we ended up with 3 equations with 3 unknowns, x, y, z. Solve it, you're gonna get a unique solution. And of course, trivial solution always exists. You see right hand side is all 0, x, y, z, all 0 is always solution. And you have 3 equations, 3 unknowns, and you're gonna get unique solution. As a matter of fact, if you want to create more equations, then all you have to do is plug in some more t values. You can create 5 equations, 10 equations, it doesn't matter. But once you reach 3 equations with 3 unknowns, actually you know, and you're going to get only trivial solution. So yes, these are linearly independent. And application for that? Oh, this is an application in differential equations. If you already took differential equation, how does some of the ideas in differential equations like Wronskian is coming into play is related to linear algebra here. But for the majority of the students, let's just move on. So what did we talk about? We talked about some linear independent concept and then went through some example problem by setting up some system of linear equations and solving x, y, z, or just x, y, or x, y, z and w, in which case it could be horrendous. But in any case, things tend to boil down to system of linear equations here. Okay. Are we ready for next topic here? No, not really. So we are done with linear dependent independence and some example, which included some highly unpleasant computation problem. And some of the homework problems that I'm going to send will be equally as bad or even worse. So please be prepared. We're going to talk about the other topics in the next video. Let's stop here.